We continue with the matrices of linear transformations, and we will generalize this now to general basis. So the topic also includes the section on change of basis. We have two vector spaces, U and V, with basis BU, ordered basis, with basis vectors U1, UN, and in vector space V, we have basis BV, ordered basis with vectors V1, Vm. And we consider a transformation T. It's a linear transformation from vector space U to vector space V. And what we did before is to define a matrix representation of transformation T with respect to the basis pair, the pair of basis BU, BV. Notation A, it's supposed to be a m by n matrix, and that it represents the transformation T. We note this with a bracket T, and then the bases are also important, BV, BU in the subscript is the notation. A supposed to be built up as the coordinate matrices of the images of the basis vectors U1, UN. The coordinate matrices in, since this is in the vector space V, there we have the basis BV. And the reason why this is nice to use this matrix representation is because then what we have is that in general, for a general U vector, in the U vector space, we can write the image TU of this vector in the V vector space with a coordinate matrix that equals to 8 times the coordinate matrix of the U vector in the U space. And again, the importance of this, that this is just a scalar vector, usually R, but sometimes we will work with complex numbers. So let me denote in general, this is Fm, the scalar field F, and it's M vector. And then this is M by N vector, the A matrix, multiplying N vector. And this works even for complex abstract vector spaces U and V. So far, if you look at the homework assignment and what we did before, we only worked with standard basis. Actually, we worked with several of them, so standard basis. And this is then quite simple to work with. As an example, in some cases, one or two cases, we even use kind of a sloppy notation without mentioning that we are working in standard basis, because it's natural that we work with the standard basis, and sometimes we omit emphasizing it. So for example, if the problem says that Txy equals to 3x minus 2y, 5x plus y, 4x minus y, and we want to figure out the matrix representation of T. First of all, what is x, what is y? Well, it's natural that xy is from the two-dimensional Euclidean vector space. And then what you see on the right-hand side is that you have 3 components. So that means T is actually a linear transformation from R2 to R3. And the fact that it's linear, you can see that the components are just linear combinations of x and y. Then the definition of A, the matrix representation of T in the standard basis, we start with the codomain basis, so it's S3, and then the domain basis S2, where the standard basis S2 is 1, 0, 0, 1, and S3 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is basic understanding that if we work with xy, it usually means Cartesian coordinates. And the definition of the matrix representation was that we have to look at the image of the basis vectors. So in the standard Cartesian two-dimensional vector space, these are denoted by E1 and E2 usually, the standard unit vectors. So it would be TE1, the image of TE1, and then the image of E2 in S3 in the standard basis. And then for E1, we have that this is 1, 0, which means x equals to 1 and y equals to 0. And for E2, we have the first component x is 0 and the second component is 1. And then we plug this into the formula for the transformation T. The way it looks right now is plugging in x equals to 1 and y equals to 0, we get 3, 5, and 4. Right now the way it's written is a row vector. And then when we plug in for E2, we plug in x equals to 0 and y equals to 1, we get -2, 1, and -1. But the notation is not really correct. The coordinate, this is supposed to be the coordinate matrix in S3, and for that we use column vectors. So basically all we have to do is turn these row vectors into column vectors. Maybe I should write here that this should be in S3, the coordinate vector or coordinate matrix in S3. So this becomes 3, 5, 4, and -2, 1, -1. So we have to be more careful with non-standard basis. For example, if T is a linear transformation from R2 to R2, actually this is written usually as a linear operator with just one space, since the co-domain is the same as the domain. If what's given is the image of vector 1, 4 as -7, 14, and the image of 4, -3 as 29, -20, you can consider this as one basis vector, and we are mapping from R2, so this would be the first basis vector, basis 1, 4 and 4, -3. It's easy to see that these are linearly independent, so that means it's a basis in R2. So if you are looking for the standard matrix of T, then the standard really refers to the matrix of T in the standard basis. So this really means that what we are looking for is, with the notation we had before, it's S2, S2, where S2 is the standard basis of R2 with 1, 0, and 0, 1. Notation for linear operators. Instead of using the same basis twice with some basis like BV, BV, we just write this down once. So no need for repeated notation. So that means that what we are looking for, the notation for what we are looking for, is that we are just looking for the matrix representation of T in the standard basis. So before we do this in general, let's look at this problem just in its simple form. So this example is not too complicated. We might be able to do it without a general formula. So if we have T of 1, 4 equals to -7, 14, T of 4 -3 equals to 29 -20, then when we are looking for the matrix of the transformation in the standard forms, then what we are looking for is a matrix so that T of 1, 4 is really 8 times 1, 4, and that equals to -7, 14. And similarly, 8 times the vector 4, -3 equals to 29 -20. Then we can put together these two equations into one equation. Actually, we can combine them together. It's not going to be a matrix vector equation, it will be a matrix equation. So the first column 1, 4, and then multiplying the 4 -3. These two vectors can be put together into one matrix, and then the right hand side vector will be actually a matrix -7, 14 and 29 -20. And you can even check that this is really how matrix multiplication works, that the first column times the matrix gives you the first column on the right hand side, and similarly the second column. We are looking for, again, this A. So how do you solve for A? We would have to divide through with this matrix, but there is no such thing as matrix division. What we have is that we multiply both sides with the inverse of the 1, 4, 4 minus 3 matrix. And the inverse gives you identity on the left-hand side, multiplying A, so that's just A. Well, let me write down that this is the A times the identity after the inverse multiplication, and on the right-hand side, you will end up with the matrix multiplying the inverse of the 1, 4, 4 minus 3 matrix. If you don't like calculating inverse, and also, as I mentioned, it's not nice, not a numerically stable operation to calculate matrix inverse in general, it's actually better to calculate this whole product in one step by using Gauss-Jordan elimination. Let me even mention that this is better to do it that way, although it's much more convenient, for example, to use MATLAB to do that, but you should still be able to solve this if needed, or for example, show the steps for the solution. It's possible to do the Gauss-Jordan elimination this way. What you're supposed to do is do a Gauss-Jordan elimination to actually get from this matrix an identity matrix. We usually do the Gauss-Jordan elimination when we have unknown vector on the right-hand side of a matrix. I prefer not to use this form because right now this has like the form of AM equals B, and this is the unknown. Usually we have something like MX equals B, where X is the unknown. So the way you can change the order of the two matrices to have this standard form where we use Gauss-Jordan elimination is that you transpose this equation. So if you have AM equals B and you transpose both sides, then you get M transpose A transpose equals B transpose, and then now this has the form MX equals B, where the unknown is on the right hand side of the matrix. So this is the standard order, at least for me. It's fine if you do it the way it is written, but I just prefer to do it this way. So what we do is we transpose and change the order. 1, 4, 4 minus 3 transpose, and then the right hand side is a matrix, not a vector. Then if I transpose this 1, 4, 4 minus 3 is actually a symmetric matrix, so it's the same as the original matrix. The right hand side one is not symmetric, so when you transpose you have to change the order of these 1, 2, 2, 1 entries. And then we do a Gauss-Jordan elimination with the augmented matrix 1, 4, 4 minus 3, and then the right hand side. It's not a vector, not a right hand side vector, it's a right hand side matrix, but the process is the same actually for Gauss-Jordan elimination, except what we get on the left hand side is the identity matrix, and the right hand side is not the inverse, not the solution, but it is the solution, but with the inverse multiplying the right hand side. So using the pivot entry 1, 1, what we need is the row 2 minus 4 times row 1. We get 0, minus 16, minus 19, 28, plus 29, so 57. And minus 56, minus 20, minus 76. Then the row 2 is divided by minus 19 to get 1 in this pivot entry. Then we get minus 3, 4. And then row 1 will be row 1 minus 4, row 2, using this as a pivot again. So this is 1, 0, 12, minus 7 is 5, and minus 16 plus 14 is minus 2. So once we have the identity matrix, we have the solution, but the solution is for A transpose. And what we are looking for is, of course, the A matrix, which is the matrix of the linear transformation in the standard basis. And that's the transpose of the A transpose, which is 5, minus 3, minus 2, and 4. All right, so this was actually done without doing the coordinate change. What we did was just writing down what it means to have this transformation. And since we had to do it in the standard basis, we do work in general in the standard basis. So once you write down the vectors, those are in the standard basis, and everything gets done in the standard basis. It is more difficult to work in the non-standard basis. Then we have the matrix of the transformation. It's supposed to be again in starting with the U basis and then taking the image and expanding in the V basis and then creating a matrix out of this. So the issue is the following. Many times we have this U and V vector spaces, and we have the BU and the BV basis. Then the question is, what happens if somehow the transformation is given in a different basis, either in the domain or in the codomain? So then what we have to do at some point is change between bases, change from one basis to other. Let's consider only linear operators so that we don't have to worry about two completely different bases. So this is from V to V, the linear transformation. Then we have two bases, B1 with U1, UN, and B2 with V1, Vn. These are in the same basis, same spaces V, so the number is the n, the same number. We did have a change of basis before for vectors. We're just going to combine it now with the transformations. So if you have a changes basis for vectors, then if you have a general vector V, you can write this in one coordinate system, for example, with U1 coordinates, with some C1, Cn vectors in the scalar field. So this is supposed to be the linear combinations of U1 and Un. And we wrote this as the basis 1, and we call this the coordinate matrix. In base 1, notation was bracket V subscript B1. We can do the same thing with expansion in B2, so then we also get B2 basis times the coordinate matrix of the same vector in B2. Then for two bases, we had transition matrix such that B1 equals B2 times Q, or if you invert, it's invertible, of course, if you have basis. Then we can also write this as B1 Q inverse equals B2. And then what we had for the vector representation is that it's this B1 VB1 can be written as B2Q times VB1, which was the same as B2 VB2. And then comparing these parts together, we also had before this that Q times VB1, which means Q times the coordinate matrix in B1 equals to the coordinate matrix in B2. So now if we apply this to linear operator from V to V, what we get is that, of course, we're supposed to have the TV's representation. For example, if the basis is B, or let's say B1 and B2. So TV, for example, in B1, the notation is supposed to be that the matrix representation in B1 times the V vectors B1 coordinate matrix. This is supposed to hold for all V vector in the V space. The same thing is true if we do this in the B2 basis. So then we get a different matrix. So these are the matrix of transformations in B1 and B2 basis. These are coordinate matrices of vectors. Then if we use this identity, so starting with the right hand side, the matrix of the transformation in B1 times the coordinate matrix of V in B1. If we multiply this with Q, then this is Q times the left hand side was the TV vector in the B1 basis, the coordinate representation. And then according to the identity here, Q times a B1 coordinate matrix is the same as B2 coordinate matrix. So we get that this is the coordinate matrix of the same vector, but in the B2 basis. Then we can use this second row here and substitute the left-hand side with the right-hand side. This is the matrix of transformation in B2 basis times the coordinate matrix in the B2 basis. Then for this part, for the B2, we can apply again this identity that the vector in the B2 basis is the same Q times the vector in the B1 basis. So the T stays there, the matrix representation of T in the B2 basis stays there, and we substitute the representation of V in B2 with Q times the coordinate matrix of V in B1. This is matrix vector multiplication, so this is associative. We can just write T B2 matrix times Q times the coordinate matrix of V in B1. And now if we compare what we started with and what we ended with, since this holds for all V vector, this is true for all V vector, that means by themselves these matrices should be the same. So Q times the representation of T in the B1 basis is the same as the representation of T in the B2 basis times Q. And then since these are matrix equations with Q invertible matrix, what we get from here is that if you want to get the matrix representation of T in a B2 basis, for example, you can solve this by multiplying with the inverse of the Q matrix. So you get Q times the matrix of T in the B1 basis times Q inverse. And this is the big formula of this section. So this comes from when we have a matrix where Q V in B1 equals V in B2, or with basis, so this is for the coordinate vectors or coordinate matrices, or for basis, the way we wrote this before is that B1 equals B2Q. Before we had change of coordinates for coordinate matrix for basis, and now we have change of coordinates for transformations. Sometimes a different notation is used where we have P equals to Q inverse. Then the same formula has the form P inverse T in B1 P results in the matrix of transformation T in basis 2. So special case is when one of the bases is a standard basis, and also when we have vector space V, which is the n vectors of the scalar field. So then if you have S, E1, En standard basis, which means that you have 1, 0, 0, 0, 1, 0, and 1. So if you collect these together, you actually get the n by n identity matrix. And another basis, B, with V1, Vn. And you have T, a linear transformation from Fn to Fn, with the standard basis representation of T being an A matrix. Then again we get the B representation using the general formula P inverse the standard representation times P, which is the P inverse A P. There is nothing new here. The only new thing is that it turns out that what you're gonna get for P is that this is the matrix with the columns V1 in the standard basis and Vn in the standard basis. Example for this, if we have T linear operator on the complex numbers and it's defined by T of Z equals 5 plus 6i times Z, and if we want to look at this in basis B, which is 4 plus 3i and 3 plus 4i. So complex numbers, the vector space of complex number is like a two-dimensional vector space, and we are looking for the matrix of this transformation in this basis. So this is like a two-dimensional vector space with the real part as a horizontal axis and the imaginary part as the vertical axis. So what we have here is, this is like a standard basis representation when we just have regular complex numbers. And the standard basis is actually the 1 and I, like it was a two-dimensional coordinate system, and we would have x and y, x equals to 1 and y equals to 1. So the 1, 0 and 0, 1 vectors for basis vectors. What is easy to get from here is the representation of the linear transformation in the standard basis, because that's just T1 in the standard basis and then Ti in the standard basis. By definition, this is the matrix of the transformation. If you substitute 1, z equals 1 in the formula, we get 5 plus 6i. And then if you substitute I, you get 5 plus 6i times I. And writing this as a column vector, this is 5 and 6. And this is minus 6. And since I times I is minus 1. And 5i, which is written as 5 in the second component. So this is what we get here, according to this previous remark here. In the B basis, we need this A matrix in the standard basis. So this is what we got right now. We don't need a notation really for that. This is T of S, what we got here. The standard basis representation of the transformation. And then we need the P matrix, which is just the vectors of B written in the standard basis. So we get this P matrix if we write 4 plus 3i in the standard basis and 3 plus 4i in the standard basis. That one is just 4, 3 column vector and 3, 4 column vector. Then with this we have that we obtain the B basis representation of the transformation by using this P inverse TS P multiplication, which is the inverse of 4, 3, 3, 4 with the 5, minus 6, 6, 5 matrix, and then the 4, 3, 3, 4 vector. I do recommend that you use MATLAB, for example, for this. This is just like too much calculation already. Although you could calculate in a few steps the inverse of this matrix and then multiply first two matrices and then the third matrix. But you're not going to get very nice numbers in some cases. Like in this case, you get something like minus 15.57, minus 21.42, 21.42, 25.57. You have to watch out for rounding error. So you use at least 4 decimal digits in WebWork, or yeah, that shouldn't be a problem. Or you can also use fractions actually. So if you calculate the inverse of 4334, you get fractions. That's actually better because then you don't have to worry about rounding error. If you calculate 4334 inverse with Gauss-Jordan elimination. Another example, for example, if you have a formula that TB1 equals 8b1 plus 3b2 and TB2 equals to 4b1 plus 7b2, then of course the question is what are these b1, b2s? It's not x and y like we used to work with, and it doesn't have to be x and y, so it's better to be precise. And in this case, for example, it turns out that b1 is a vector minus 1, minus 1. b2 is another vector, 1, 2. These are all in R2. And since -1, -1, 1, 2 are not collinear, we have that when you put these together, you get a basis in R2. If you define T this way, in this basis, you get that T is a linear operator on R2. So then the matrix of this in B, the image of the basis vectors expanded in the basis B, but this is 8b1 plus 3b2 expanded in the basis B, and 4b1 plus 7b2 expanded in the basis B. Okay, so if you need practice how to expand, how to calculate the coordinate matrices in basis, please go back just a few sections before. It's supposed to be a coordinate matrix. It's a column vector, actually, collecting together the coefficients of the two basis vectors. So it's 8, 3, and then 4, 7 in column vectors. So you end up with a matrix. So that's kind of trivial. You just collect together the coefficients. But now the question is then, what if you want to go back and get the matrix in the standard basis 1, 0, 0, 1? Sometimes also the E notation is used for that. So we have the standard basis and another basis. We can use this formula in some way. Maybe you have to rearrange it. So the formula was that the matrix in the B basis is P inverse the matrix in the standard basis times P, and P is the matrix of vectors, basis vectors written in the standard basis. So right now actually we have only two vectors, B1 and B2. Those are written in the standard basis already, -1, -1 and 1, 2. Yeah, so when we said that B1 is the -1, -1 vector, this is what we really meant here, that this is in the standard basis. It's hard to talk about R2 without using the standard basis. And we already calculated the matrix of the transformation in the B basis. We didn't really have to calculate, we just had to collect together the coefficients, 8, 4, 3, 7. And then what we get is that P inverse -1, 1, -1, 2. And we are looking for the matrix in the standard basis. And that's supposed to be inverse. So if you multiply from left with the matrix and from right with the inverse of this matrix, then we get the standard basis representation. So from left we have to multiply with the matrix in order to get rid of the inverse. And from the right we have to multiply with the inverse. Let me do this very quickly. So first of all, you can multiply this together. These two matrices, we get -8 plus 3, that's -5, -4, 7, 3, -8, 6, -2, -4, 14, 10. And then the inverse of the matrix, -1, 1, -1, 2. Very quickly, 1, 0, 0, 1. You get from here -1. Well, I can do maybe 2 steps in one. -1, -1. Then we add this to the second row. 0, 1, -1, 1. And then we subtract, or we add the second row to the first one. We get 1, 0, -2, 1, and 0, 1, -1, 1. Since we got the identity on the left, this means that that's the inverse. -2, 1, -1, 1. It's actually, it's fast to invert it. And then just multiply together the two matrices. We get 10, -3, that's 7, -5, 3, -2, 4, -10, -6, and 2, -2, 8, -2, 10, 8. And we got the representation in the standard basis of the linear transformation. Abstract, more abstract vector spaces. If the linear transformation, sometimes the notation is L, that stands clearly for linear. And for example, if we go from P4 to P3 polynomials defined by multiplying with -8 the derivative of P plus 4 times the second derivative of P. So this is from P4 into P3. First, the basis that we want to use is in P4, the standard basis E that has now order x cubed, x squared, x and 1. And in P3, non-standard basis, again ordered x squared plus x plus 1, x plus 1 and 1. It will be a short exercise to check that this is really a basis. So we are looking for the representation as we go from E to F, from P4 to P3 of this linear transformation. So by the definition, this is supposed to be a matrix where we use the basis vectors. We apply the transformation to those basis vectors in E, and we expand this in the new basis F. So first of all, we have to differentiate and multiply, and that takes actually some time to calculate. L x cubed is -8 times the derivative, which is 3x squared, plus 4 times the second derivative, which is 6x, and this is -24x squared plus 24x. The problem with this that this is right now this can be written in the E basis easily. So in the E basis, this would be 0, -24, 24, and 0 in E, using the coefficients for x cubed, x squared, x, and then for 1. But unfortunately, that's not what we need. We need the coordinate matrix in F. So let's continue with that later. And right now, let's calculate the linear transformation for x squared. It's -8 times 2x plus 4 times 2, which is -16x plus 8. Then Lx, -8 times 1 plus 4 times 0, so it's -8. And L1, the derivative and the second derivative of 1 is 0, so it's 0. So similarly to the previous coordinate representation, we could write this that this is 0, 0, -16, 8 in the E standard basis. This is 0, 0, 0, 8 in E, and this is of course just the 0 vector in E. So if we collect together these vectors, what we get is that in P3 and in basis E, the standard basis, we have Lx3, Lx2, Lx, and L1. No x3, no first row. We get -24, 24, 0, 0, -16, 8, 0, 0, -8, and 0, 0, 0, which just means that 1 is in the actually null space. We can expand also F in E, which means the change of basis, really. So F was the basis x squared plus x plus 1, x plus 1, 1, which in the E basis, using standard coordinates, this is 1, 1, 1, this is 0, 1, 1, and 0, 0, 1. Again, this was in an E basis, the standard basis. If you want to change to the F basis, what we have is that F basis is really E times, not to confuse what is P and what is Q. Let me just use the notation B for this one. So this is E times B. If you look up the basis change, then this was actually the notation Q. And what we had is that if you have a basis change, for basis, if you have this F equals to E times Q, change of basis, then when you want to change coordinate, then in the F coordinate you have Q multiplying from the left, and then you get the coordinate matrix in basis E. And if you want to get then the coordinates in F, that means that you have to multiply with the inverse of Q from the left, the coordinate matrix of E. Since what we had here is the matrix of the transformation in E, that means that to get the matrix of the transformation in the basis F, we have to multiply with the inverse of this matrix the representation of the transformation in the E basis. Inverting this 1 0 0 1 1 1 0 1 1 matrix is not that difficult. It's actually nice to practice this. So we have to subtract from the second row. The first row we get 1 0 0 1 0 0 0 1 0 minus 1 1 0. Then we have to subtract this and the first row from the second row, from the third row. We have to subtract from the third row this first row and the second row. We have to subtract from the third row the first row and the second row to get 0 0 1. So subtracting it, we get 0 here, minus 1 and 1. And this is already the identity, so this means that this is the inverse. So we get for the F representation that this is 1 0 0 minus 1 1 0 0 minus 1 1, multiplying the matrix in the E basis, which was minus 24 24 0 0 minus 16 8 0 0 minus 8 and 0 0 0. And then what we get is minus 24 0 0 0, 24 plus 24 48, minus 16 0 0, minus 24 16 plus 8 24, minus 8 0, which is what we were looking for. So it's an interesting question, why would you need this F basis? But there are some reasons in some computations why you want to use non-standard basis. The nice thing about this is that if you want to use this new basis, for example, if you want to calculate LP in the F basis, if P of x is minus 3x cubed minus 5x, what we calculated here, really, it's not exactly the representation in F. It is the representation in F, but we were going from E to F, since L is from P4 to P3. And in P4 we use the standard basis, and we use the non-standard basis in the P3 basis. Then we can write this P minus 3x cubed minus 5x in the standard coordinates in P4. So in P4 this is minus 3 0 minus 5 0, and then LP in the F basis will be simply the L matrix representation when we go from E to F basis between P4 and P3 times the representation of P in the E basis, which is simply the matrix multiplication minus 24 48 minus 24 0 minus 16 24 0 0 minus 8 and 0 0 0, multiplying the minus 3 0 minus 5 0 vector So this is minus 3 times minus 24, that's 72. Then minus 3 times 48, that's minus 144. Minus 3 times minus 24 is 72, plus 8 times 5, 40. So it's 112, which means that it's just a simple matrix vector multiplication, the differential operator. You can actually check your answer if you apply LP. So that was the formula was minus 8p prime plus 4p double prime. This is in this case minus 8 times you differentiate p, you get minus 9x squared minus 5, plus 4 times you differentiate one more time, you get minus 18x. So altogether you end up with 72x squared plus 40, and then minus 72x plus 40. While calculating this from the f coordinates, in the f basis, this says this is 72 times the f basis was x squared plus x plus 1, the first component. Then the second component that has multiplier 144 was x plus 1, and the third component was just 1, and that multiplies 112. And if you do some simplification here, we still have 72x squared, then 72x minus 144x is minus 72x, and then 72 minus 144 is minus 72, plus 112 is plus 40. So we get the same answer in two different ways.